up. So maybe when the students they talk to us. Right. Good morning to you all. Sorry, there seems to have been a bit of a confusion about the timing for this morning. So let me just repeat in general that Monday is 8 a.m., Wednesday is 8 a.m., but Tuesday and Thursday classes start at 9. Okay, so that you are not sort of confused about the time arrangement. This is chemistry 102. I'm not sure what time you have GST, but this is CHM 102. All right, so we had gone as far as looking at the first family of organic compounds, the most basic of them all, the alkanes. And looking at we talked about the general chemistry of the family. We looked at their abundance or presence in nature, looked at their nomenclature, physical properties, and we ended up that yesterday with the chemical properties or reactions. I'm aware the coordinators needs to organize for you to have access to my own specific materials. So I'm sure he will do that today, between today and tomorrow. Okay. So we are starting today with alkenes, the second family of organic compounds. Again, not something strange, because you definitely have come across alkenes because you've all done chemistry before now. Now, so in simple terms, alkenes, also known as olefins, are unsaturated hydrocarbons. Okay, they have at least one double bond. I say at least because you can have a compound that has more than one. Okay, it can be a diene, that it has two double bonds, or a triene to have three double bonds, and so on and so forth. Okay, for the carbon double bond, the two carbons carrying double bond, they are actually sp2 hybridized. Okay, those particular carbons are sp2 hybridized, and so it means that at those carbon atoms, for instance, you cannot have a chiral center. Remember, I said chirality is linked with the type of hybridization. It must be sp3 hybridized for it to be a chiral center. So alkenes, for instance, where you have the C double bond C, definitely cannot be one of those chiral centers. They have general formula CnH2n, okay? And so it means that once you know the value of N, you're able to tell us the number of hydrogen atoms expected for a particular alkene. The double bond is made up of one sigma and one pi bond. Remember that in alkanes, you have only sigma bonds all through the molecule, but with alkenes, you have at least one sigma and one pi bond where you have the C double bond C. Of the two bonds, the pi bond, of course, is weaker. And in this case, remember that because of the type of hybridization, remember you looked at hybridization with the earlier lecture, Professor Ajayi taught you hybridization. The basic context here, or what is sort of important to us on this side, is that there is actually a difference as a result of those hybrid orbitals in the carbon-carbon bond length. Okay, the carbon-carbon bond length for ethene, okay, is 1.33 angstrom. Okay, so I'll need to correct that. That should be ethene, not ethane. Okay. can say clearly this is ethene. Okay, while that in a regular carbon of ethane is 1.54 angstroms. Okay, angstrom is the basic unit we use in measurement of bond lengths. Now, so beyond the general chemistry, okay, which we have just talked about, the fact that they have double bonds, they have general formula. Alkenes are very useful. They are useful in drug and pesticide industries. Ethene, in particular, is used in ripening of foods, in preparation of solvents that are used in the lab. Other members, ethene, propene, are also useful in the polymer industry. We use them. I'm sure you've come across polyethylene or polypropylene. Okay, those are compounds derived from this family of compounds. Now we're going to the nomenclature. Okay, how do we name these compounds? Well, like I said, I know you are very used to IUPAC. We do not only use IUPAC in advanced level work. Common names are still used, and we use them most of the time with simpler alkenes. So ethene, for instance, is called ethylene. And you heard when I said, I'm sure you have come across polyethylene. Okay, I'm sure you know that those ones used as polymers, a lot of time they still use some of these older names. So polyethylene from ethylene, propylene, that's what we popularly call now propene. Then vinyl chloride, okay, that's chloroethene, and bromide, for example, that is bromopropene, okay, 2-bromopropene. So those names are still valid. They're still, you still need to be familiar with those. But of course, the IUPAC nomenclature will suffice for bigger, larger, more complicated, more substituted types of alkenes. IUPAC naming is the most common way, okay, of naming them. And again, what we do is to find the longest continuous chain of carbon that has the C double bond C. Okay, so in this case, we're not just looking for the longest continuous chain of carbon, we're looking for the longest continuous chain of carbon that contains the functionality, the functional group. Okay, and that would, of course, make them different from alkanes, where we are not interested in any particular, just carbon and hydrogen also. So in this case, if you look at the example on the slide, in this particular illustration, the C double bond C, which, well, I will say that in a short while needs to have its smallest number possible. If I number, sorry, there should be 6, there should be 7. So if you number that way, then you'd realize that I've of course numbered in such a way that the C double bond C is included in that my longest chain of carbon, because if you're not looking at that longest chain of carbon that has the double bond rather, if you're not looking at that, then you realize there's another way to number and the chain will be longer. But in fact, because it must contain the C double bond C, then this example actually shows us that we have to make the longest chain this 7-carbon chain. So since it's a 7-carbon system, that will be hept, okay, for 7, and then heptene because the compound is an alkene, and the double bond is on carbon 1. Okay, the double bond is on carbon 1, so it will be 1-heptene. So what is left now is to identify what is the substituent to this our 1-heptene. So at position 3, we have a propyl group. So we just say the full name of the compound will be 3-propyl-1-heptene. Okay, 3-propyl-1-heptene. So the first thing there is to again identify the longest continuous chain of carbon and name it, replacing the N of the alkane, ENE, for an alkene. Number 2, number the parent compound from the end nearest the C double bond C. Okay, and that's why you see that in the previous example, I started the numbering from, since the carbon C double bond C is actually terminal, I started numbering from that end. That's why I called it 1. Okay, so we have to number from the end nearest where we have the double bond. If it is even, that is, if the double bond is in the middle, then we number to give the lowest sum for the substituent. So if our double bond is actually in the middle of the molecule, then the numbering should be done in such a way that if there's any substituent alone, so if there is a substituent, then we'll look at the position of that substituent and ensure that that numbering gives that substituent the lowest number possible. So if you look at this, we have to number from this end, despite the fact that the molecule has 8 carbons, and of the 8 carbons, if you number from whether left or right, the double bond will be on carbon 4. Okay, but in this case, because there is a substituent at position 2, if you number the way I've numbered now, then this will be the correct number. So it should be 2-methyl 4. Of course, this is an 8-carbon system with the double bond at position 4. So it will be 2-methyl 4-octane. Okay, so that just shows that the numbering has, in this case, favored where we have the substituent. So the substituent has the lowest number possible. Then we need to ensure the use of an appropriate prefix to indicate the stereochemistry of the alkene. The lack of easy rotation about a double bond gives, of course, what we have talked about before, configurational isomers. Okay, and so the cis-trans possibility is real. So if we have, okay, like in this the example on this slide, 2-butene. Now for 2-butene, you can have it written in such a way that the 2 groups are on the same side. You consider up and down now. The 2 CH3s, remember that these are CH3s. That is also a CH3. The 2 CH3s there are above the plane, if you consider it to be, a middle plane. And you can also write it in such a way that the 2 CH3s are below. So whether we draw it the way it has been drawn here, or it is drawn, okay, written in that other form, both structures refer to cis-2-butene. Okay, but in the case of trans, one will be, quote, facing up while the other is facing down. They'll be on opposite sides. Okay, so again, it's important to ensure that when you are looking at whichever molecule you are looking at, you can easily, see that, okay, are they facing the same side from a particular plane? I mean, looking at the plane of the double bond, or are they facing opposite sides, looking at it from the plane of the double bond? And I said, note for an alkene, okay, to have geometrical isomers, then the group attached to both carbon atoms bearing the double bond have to be different. In other words, there is no isomer of propene. And the reason is because if you look at propene, on one carbon, you have 2 hydrogens. One carbon carrying the double bond, you have 2 hydrogens. On the other carbon, you have a hydrogen and a methyl. So in that case, we are not expecting that it will have geometrical isomers. For it to have geometrical isomers, then the groups that are attached will have to be, so in case, maybe a good example then will be, you have a CH2 on one carbon, the other carbon carrying a double bond can have 2 CH3s. And of course, that's what we have in the case of, okay, not exactly the case with butane, but what I mean is that if, let me use this as an example. Okay, so rather than having, so you can have a system like this. If you have hydrogen, hydrogen, okay, then of course you're going to have geometrical isomers. If you also have, if it is chlorine, chlorine, you're going to have geometrical isomers. Okay, but once you have a case where you have maybe this one of these hydrogens is now a different thing, maybe a CH3. Okay, then you have a situation where you are not going to have geometrical isomer. There's a different way we use in naming this, but we leave that. We teach that at a level above where we are now. All right, so that is all in terms of nomenclature of alkenes. Maybe I could quickly give us our first code for the day. So it is R for room, K for kite, R for room again, N for Nigeria, Y for Yale. RKRNY. RKRNY. Okay, thank you. So a few of you already have the correct code. Yeah, that's correct. RKRNY. All right. Again, we're looking at alkenes. I see a few people have asked, what's the topic? It's alkenes. We have left alkenes now, and we just finished considering of course, apart from the general chemistry, we talked about the nomenclature. And under nomenclature, I said again, we trace the longest chain of carbon, find out, and we number in such a way that the double bond has the lowest number, and then we try to establish if there is any form of geometrical isomerism, in which case it will either be cis, okay, for instance, 2-butene, cis-2-butene, or trans-2-butene, okay? So we go into stability of alkenes. Now, the position of the double bond vis-a-vis the number of substituents you have around the group or in the particular molecule you are looking at determines how stable it is. So if you look at the order that I have on this slide, this indicates the stabilities of different alkenes. Okay? And it means that this order tells us what is likely, to prevail when you are trying to, when there's a possibility of either having one type of alkene or the other. And we'll get, when we start looking at their reactions, you will see why this is a very, very critical background to have. So in general, a tetra-substituted alkene is more stable, okay, than a tri-substituted alkene, which is more stable than, if you look at the example on the left, the third example here is a disubstituted alkene. But in this case, the disubstitution is such that the substituents the R groups are on one carbon and the other carbon has hydrogens. Now that is more stable than when you have a trans substitution. Again, this is disubstituted. So there are three types of disubstitution that I'm showing here. Okay, the first one where we started on the left, on the far left, is tetra substituted. The next was tri substituted, but the three that now follow are all disubstituted. The difference is where the R groups are located. In the first case, the two R groups are located on the same carbon. Then in the next two cases, they are located on different carbons. But the first one is trans geometry, and the next one marked X, is cis geometry. Okay, so that is the order of stability. So you can see that your trans, okay, is actually more stable than your cis. And if you remember what I explained in terms of repulsion of bulky groups when they are next to each other or when they face each other, when we're looking at eclipse systems, you might be able to quickly grasp why that is. So, and that, of course, the cis is more stable than the monosubstituted, which, of course, is more stable than an unsubstituted alkene. All right, so I have a simple illustration here. That question says, when an elimination reaction of an alcohol takes place, an alkene product is formed. These reactions are regioselective, meaning one constitutional isomer is formed preferably over others. Please rank the following alkenes in order from least stable to most stable and justify your answer thoroughly in words. So if you look at those 4 options there, the least stable, remember from the order I gave you in the on the previous line and on the slide, when you have monosubstitution, it is less stable than when you have disubstitution. Okay, so if you look at option A, how substituted is option A? Is it mono, di, tri, or tetra? Option A, is it mono, di, tri, or tetra? Yeah, somebody should respond to that. A is mono. Okay, thank you. All right, so because there's only one substitution at that double bond. Okay, so if you can figure out that A is mono, then you know that A, of course, should be the least stable. Okay, since there's no case of unsubstituted here. Okay, so the A will be least stable. Then we look for which one has double substitution. Okay, if you look at D very well, you see that D has double substitution. Are you following? And then if you look at option B, you see that it has it's a tri-substituted alkene, and option C is tetra-substituted. So again, you need to reflect that in answering that question correctly. But this just shows that, in fact, the stability of alkenes is something that we need to understand. Now we go on to preparation of alkenes. The first method we'll look at is dehydrohalogenation of alkyl halides. So look at dehydrogenation means we're removing a hydrogen and a halogen. Okay, so that process requires that we have a strong base. Okay, in this case, we would normally use hot ethanolic KOH or potassium ethoxide. So as you can see on the equation, if this alkyl halide that's chloropropane is to be treated, what you would have at the end of the day is that a hydrogen from here and a chlorine from there are going to go. Okay, it's an elimination reaction. Okay, so you are going to lose a hydrogen and a chlorine, and we lose them in such a way that it is the group that is on the other side that we actually lose. So the hydrogen below and the chlorine above will go and then lead to giving us propene as our product. Now, that reaction is such that, yes, in a case like this, you can have a simple product. It is only one likely possibility, okay? But there are cases where you can have more than one, and that will depend on the kind of alkyl group you have. So for example, if you look at 2-bromo, 2-methyl butane, okay, in the next equation on the slide, you realize that this can actually give us 2 possible products, okay? In the one case, remember I said we're going to lose a hydrogen that is, well, the word is adjacent to the halo group. Hydrogen that is adjacent to the halogen. So if you lose hydrogen from the carbon here. Okay, remember there's one hydrogen above the plane, there's one below, technically. If you lose the hydrogen from that carbon, the carbon next to the carbon carrying the bromine, then you would end up with 2-methyl-2-butane. Whereas you can also lose hydrogen from any of the methyl groups next to the carbon carrying the bromine. If you lose hydrogen from any of those methyl groups, then you end up with the second product here, that's 2-methyl-1-butane. Now, look at the yields of the two. Those percentages given below are the yields. That is, when you carry out the reaction, we have 69% of the product being 2-methyl-2-butene and 31% of the product obtained being 2-methyl-1-butane. Now, the first thing to look at here is for the 2-methyl-2-butane, as you can see, it is in terms of stability. Is it more stable or less stable than the 2-methyl-1-butane? Look at the double bond position. At that double bond, this 2-methyl-2-butane is tri-substituted. And at the double bond on 2-methyl-1-butane, it is di-substituted. So again, 2-methyl-2-butane is more stable. And because it is more stable, it explains why it is formed in higher percentage. Okay, so I'm trying to help you see where this stability thing also plays out. Of course, if we're showing how the reaction is formed in terms of the mechanism, you also see why the system leading up to the formation of 2-methyl-2-butane favors 2-methyl-2-butane as the product. So I said the transition state leading to the formation of 2-methyl-2-butane is more stable than that leading to 2-methyl-1-butane. All right, and so we obtain 2-methyl-2-butane in more concentration, in more yield, not concentration, more yield. Okay, number two, second method of preparation of alkenes, dehydration of alcohols. Again, I know you have come across this one. It's very clearly spelled out in Ababio. Again, alkenes also, you start doing them from secondary school, so they are less scary grounds to operate in. So for dehydration, we're talking about removing water. All right. So if we heat alcohols in presence of a strong acid, they tend to lose water. And of course, the most simple example of that is when we heat ethanol. When we heat ethanol, it loses water to give ethane. So it's also an elimination reaction. In this case, it's favored by high temperature. Now, in the lab, we would use Bronsted acids such as sulfuric and phosphoric acids, but alumina could also be used in general. And so what I try to show below is, so for every organic reaction, there is normally a step-by-step process of what goes on. I know you looked at some types of basic reaction kinetics in first semester. Okay, you look at kinetics of reactions, and then you are told some of the elementary steps that lead up to a particular reaction. Now, so in this case, what we're also still talking about is some of those elementary steps, the steps that lead up to a specific reaction that we write in the form of an equation. So if you look at ethanol, okay, right under where I wrote mechanism, you see that I try to emphasize that the hydrogen and the hydroxyl, okay, from the two adjacent carbon atoms will come off in the process. But what happens first is that in the presence of the acid is indicated by the H+, the OH the hydroxyl group, is protonated. When that happens, it means that the OH, which is lone pair of electrons, with the lone pair of electrons on the oxygen, it picks up that hydrogen ion. When that happens, you have the formation of OH2. Okay, that OH2 there is showing that it will carry a positive charge, a formal positive charge, because now you have formed water molecule, but that water molecule is connected to the carbon system. So that oxygen will have a formal charge of +1. Now, because water is a neutral molecule, water will be a relatively good living group. Okay, and so the water leaves with the electrons with which it is bonded to the carbon. With that, those electrons then neutralize the positive charge on the oxygen, and then you have a neutral molecule of water coming off that system. And so you are left with a CH3 that is now connected to a carbon center that is positively charged. What do we call this type of positively charged carbon center? Somebody? What are they called? I want to be sure you were following Professor Ajayi's lecture. What do we call a carbon atom carrying a positive charge? You should have, I'm very sure you must have treated. In fact, someone said they've been taught when they were in secondary school. You see, I know we are repeating, but it's fine. It's not cation, it's carbocation. Okay. Yes, thank you. That's the word I was waiting for. Carbocation. Sorry, I know the response is a bit slower, but I have to still try to be sure that we are following. So the CH3 connected to a CH2 carrying a positive charge is a carbocation. And so what then happens is that it loses a proton. When in the loss of that proton, we then have the formation of the alkene. All right. So yes, that's how the dehydration mechanism actually is. This is just to help us remember that that water comes off such that we lose a hydrogen from one of the carbons and the hydroxyl from the other carbon atom. Okay. The third method of preparation is dehalogenation of vicinal dihalides. You can have vicinal dihalides. Okay, sorry, let me give us the next code. It's nice to give us the codes when we are right about the middle. Second code for today is V for violin, W for wall, figure 8, L for lion, F for fame. VW8, LF. VW8, LF. Thank you. Okay, I see a few of us have that already. All right, so I can go back to the lecture. So I said the third method of preparation of alkenes is dehalogenation of vicinal dihalides. Vicinal dihalides simply refer to alkyl halides that are actually dialkyl. Sorry, they are alkyl halides that have two halo groups. So if you call them haloalkanes, they are dihaloalkanes. That's what I wanted to say. So in this case, you have two bromine atoms, for instance, connected to two adjacent carbon atoms. When you have such, the two bromine atoms can actually be removed, okay, by reduction with either iodide okay, in acetone, so sodium iodide, for instance, in acetone, or zinc in acetic acid. Okay, and I tried to show the equation for both on this slide, showing that essentially what is happening is that the two halogens are mopped up by the reagent. So if you're using sodium iodide in acetone, you see it forms IBr plus NABr as a side product. If you're using zinc in acetic acid, it forms zinc bromide. Okay, but essentially they reduce the dihaloalkane to give us an alkene. All right. And then the fourth method of production of or synthesis of alkenes is partial reduction of alkynes. Now, partial reduction, of course, has to be done in a very careful manner. Remember, you are going from a triple bond to a double bond. And if you are not careful, it can go from that double to single bond. So it has to be done in a very careful manner under controlled conditions. But yes, you can go from ethine to give ethene, okay, under controlled conditions of hydrogenation. Now, of course, some alkynes can be reduced to give either the cis or the trans. Okay, so for instance, starting with 2-butyne, if you use sodium in liquid ammonia, you end up with the trans product. Okay, if you use hydrogen with Lindlar catalyst, you end up with the cis product. So again, we can play around with what we call the region of the molecule, where how the double bond aligns. Okay, so you can go from that linear 2-butyne to actually give the trans or the cis product for the alkene that is formed. All right, so any of these methods are useful in terms of making alkenes in the laboratory. So we go on from their preparation to looking at the properties of alkenes. Alkenes, just like other hydrocarbons, are nonpolar in nature, and the lower members, carbon 2 to carbon 4, are gases. From carbon 5 to 17 are liquids, and then 18 and above are actually solids at room temperature. Now, they tend to bond because of the degree of unsaturation. Remember, the C double bond C is an example of an unsaturated system. Okay, so because of that degree of unsaturation, they bond in air with what we call a luminous flame, okay, or a smoky flame. They are insoluble in water in general, but they can be soluble in non-polar solvents. Okay, they are less dense than water, and they have boiling points that are lower than the corresponding alkanes. So we'll go on to their chemical properties, or what we call their reactions, reactions of alkenes. Number one, they undergo what is called addition reaction. Remember, at the beginning, we talked about types of organic reactions. And at that point, I did mention that you have not just substitution or elimination, you also have what you call addition. And the last of them was rearrangement. So the pi bond is particularly susceptible to electron-seeking reagents. And so they tend to react with electrophiles, you know. So if the first class of addition reaction we'll look at addition reaction with symmetrical reagents. Okay, so reagents that are symmetrical. If you can use a middle line to say that the left and the right are the same. For instance, hydrogen molecule, okay, is hydrogen connected to hydrogen. So it's symmetrical. Now, reduction with hydrogen or reaction with hydrogen simply will be effected in the presence of a catalyst. This actually requires a catalyst. So either platinum or nickel or palladium can be useful for this reaction. And what happens is that the hydrogen adds to one side, or what you call one phase, of the double bond. So what I mean is the two hydrogen atoms actually add from one end, okay? I'm trying to show you that if it's coming from below, as it were, the two hydrogen atoms will add from that same phase, okay? So it's a same side, or what we call a syn addition, SYN. It's a same side or a syn addition, okay? And that's how reduction with hydrogen takes place. Now, the opposite of syn addition is anti-addition, okay? And what I've done here is to try and show so that you understand what exactly is taking place. So with a syn addition, you see that if it's generally X and Y, they add from that same phase, okay? And I'm using the three-dimensional illustration so that you can really understand what is happening. So the X and Y both come from underneath, as it were, and they add that way. But when you have what is called an anti-addition, then X adds from one side while Y adds from the opposite side. Okay, so if X is adding from beneath, then Y will be adding from above. All right, so that leads to this type of anti-product. Now, still under symmetrical reaction with symmetrical reagents, addition reaction with symmetrical reagents, we have halogenation. Okay. Now, alkenes react with mostly bromine and chlorine to form vicinal dihalides. Remember, when we were talking earlier, we talked about vicinal dihalides in terms of making alkenes as well. So this reaction, when bromine is used, actually serves as a test for unsaturation in the lab. I'm sure you know that, and you might have even, okay, well, you've had some problem with your practicals. I don't think many of you have done some of the practicals yet. But indeed, this test for unsaturation is one of the things you will do in the lab. And what happens is when you subject the alkene, if it is an alkene or if it carries a double bond or contains a double bond, if you react it with the bromine, which normally is either they would have put it in some form of solvent or a non-polar solvent that will hold it in place, the reddish brown color of the bromine is lost. We call it disappearance of that color. It's actually one of the tests for unsaturation that we use in the lab. Okay, so as bromine molecule approaches the alkene, essentially what happens is that you have a polarization of the bromine such that one of the bromine atoms, and I'll continue explaining this on the next slide, will take a positive side while the other will take a negative side. So if you look at, I've moved to the next slide and I'm still trying to illustrate that same point. If you look at the double bond, okay, as the bromine molecule here, as that bromine molecule approaches, what happens is that the bromine, which has what we call polarizable bond, it has a polarizable bond, then tends to add in such a way that one side, the one above, okay, is able to receive electrons from the C double bond C. And then you have, so as the electrons come in, it pushes away the other bromine as a bromide. Okay, remember that it's a bromine-bromine single bond. but the bromine below, the one that is not the one next to the double bond now, will come off as a Br minus. Okay, but the one above, when, remember, you are starting from a neutral molecule, but we're saying that that neutral molecule can be polarized such that one becomes positive, one becomes negative. The two bromine atoms, one takes plus, one takes minus. The one that takes plus adds to the ring, okay, adds to the double bond to now form a ring. Okay, that ring is what we have here. Okay, now that ring, of course, is kind of positive charge, overall positive charge, because the Br there is positive. The Br minus that comes off then adds from the other side after this intermediate, the three-membered ring, after containing Br. After that intermediate is formed, then the Br minus adds from the other side. And when it does, you end up with a product in which bromine has added to the double bond, but has added from both faces, has added from below and from above. Okay, so this is just trying to show or illustrate to us how that happens. Okay, so that you're able to at least conceptualize it to understand why we have a bromo where both of them are not coming from the same side. So remember that with hydrogenation, it came in from the same side. However, with bromination or halogenation, you actually have a different side addition. What I said is an anti-addition. So with hydrogenation, you have a syn addition. With halogenation, you have an anti-addition. Okay, and that just shows. Now, a quick example to illustrate that is addition of bromine to cyclohexene. Okay, this cyclohexene here, you can see cyclic with a double bond, so we call it cyclohexene. If you react that to the bromine atoms will add, like I said, in an anti fashion, such that one of the Br coming in is on the face, the side facing the reader or the author, and the other is on the opposite side. Okay, so that's why we have the two Brs, one with a wedged bond, one with a hashed wedge bond, meaning that it's actually a trans dibromo product that we end up with. Okay, just illustrating the fact that bromine addition happens in a trans or an anti fashion. All right, so we've looked at symmetrical reagents. Now we go to unsymmetrical reagents adding to the double bond. Remember, we're looking at reactions of alkenes. Okay, so in the first case, we look at where you have hydrogen or say bromine, for example, or chlorine as the reagents we're adding. Those were symmetrical. Now, when you talk about unsymmetrical reagents, the first example we'll look at is hydrohalogenation. Okay, hydrohalogenation. And that simply means we're adding HX, okay, to the alkene. Now, by HX, I mean where X, of course, represents the halogens. Okay, so either HI, HBr, HCl. But the general order of reactivity is such that HI is greater than HBr, greater than HCl, greater than HF. Okay, I need you to see that. And unless the alkene is highly substituted, HCl can actually be quite slow. So when we add HX rather, when we're doing the addition of HX to unsymmetrical alkenes, by observing that reaction over and over, an old chemist, well, back in the days, a Russian chemist by the name Vladimir Markovnikov came up with a representation or a basic rule that guides what goes on in this system. And the rule simply states that ionic addition of an unsymmetrical reagent to a double bond, that in that process, positive portion of the adding reagent attaches itself to a carbon atom of the double bond so as to yield the more stable carbocation as the intermediate. Okay? So that's the statement, but let's talk about it in practical terms now. So you're adding HX to an unsymmetrical reagent. So remember, if you're adding it to ethene, which is a symmetrical alkene, then there is no problem. The H and the Cl will just go to one other side. But when you are adding HCl to propene, propene is not symmetrical. That is, if you put a dot like that across propene, the left-hand side and the right-hand side are not the same. Okay? So what that means is that when you have this type of addition in an unsymmetrical alkene, and we are using an unsymmetrical reagent, what the Markovnikov rule states is that there is an order in which the reaction will follow. And the order is such that when the double bond picks up the H, now you have HX. In that HX, our H is the electrophilic side. Our X is the nucleophilic end. Okay, remember that halides are electron rich, they pull electrons towards themselves. So the H is electron deficient. So with the rich electrons of the alkene will pick up the H. When that happens, you can have two possibilities. If it picks up the H so that the hydrogen adds to carbon 1, then you end up with the first carbocation illustrated here. Okay? On that first carbocation, the positive center, remember that when that double bond picks up the hydrogen, there's nothing on the other end. And so you have a positive center. Meanwhile, it could also add such that the hydrogen adds to carbon 2. And then the positive center will be at position 1. So, but if you look at one intermediate above and intermediate below, in one case, the carbocation is secondary, while in the case below, the carbocation is primary. Of the two of them, of the secondary and the primary carbocation, which one is more stable? Which carbocation is more stable? As I look for your third code. Yes, you must have done stability of carbocations earlier. Okay, the third code is Y for Yale, T for top, figure 9, A for apple, B for ball. YT9AB. YT9AB. No, not G. YT9AB. Okay, I think a few people have it correctly now. Yes. YT9AB. Thank you. Okay, my question was, yes, please, the coordinator will ensure you get the slides. I will try and see if he can do that today. I'll talk to him and he'll find a way of getting across the slides to you all. Okay, so I asked that which one is more stable. Okay, so somebody said secondary. Okay, I saw secondary. Some said the one above. Okay, so that's correct. So the one above, the secondary one, is more stable than the one below. And that's why I said it is the one above that the chloride is going to then attack, not the one below. So the not that I put here is trying to show that not the primary carbocation, but rather the secondary carbocation is the one that the chloride would then attack. Oh, and I'm sorry, the product I wrote is having bromo. Sorry, this should be Cl, not Br. Okay. All right. But I hope we get the point. And the point is that According to the Markovnikov rule, if this reaction happens between HCl and propene, then our product should be 2-chloropropane. 2-chloropropane. Again, another example beneath that, you have, this is 1, 2, 3, 4. So you have 2 sorry, 1, 2, 3. So the methyl group, sorry, is actually, so we have 2-methyl propene. Okay, 2-methyl propene. The HBr is adding to the 2-methyl propene. And if you look at it carefully, you realize that the most stable carbocation will be this carbocation, okay, which is a tertiary carbocation, okay, rather than saying that, okay. The most stable one is the first one that I wrote out. And once you have that stable carbocation, then the Br minus then attacks at that middle carbon position, giving us this product. Okay, so again, even though I know you would have done that before, I still went ahead to state the stability of carbocations for referencing. So at least you can still see it within this slide as well, that the tertiary carbocation is more stable than the secondary, which is more stable than the primary carbocation, which of course is more stable than methyl. Okay. So when a reaction can potentially yield 2 or more isomers, okay, but when it produces 1 predominantly or majorly, such a reaction is said to be regioselective. Okay, and a good example is addition of HX or hydrohalogen to unsymmetrical alkenes. Okay, is said to be a regioselective reaction. Now, the addition of HI, for instance, to 2-methyl-2-butene gives 2-iodo-2-methylbutane as the major product. But what I want you to understand is that there will still be some of the minor product as well. But we normally concern ourselves with, okay, based on stability, based on the carbocation that is generated, the major product should be, in this case, 2-iodo-2-methylbutane. But just to make you realize that in practical terms, in reality, some of the 2-iodo-3-methylbutane is also formed. Okay, we call that the minor product, and the one that is formed in higher quantity is called the major product. So you have the major and the minor product for such a reaction. Okay, so again, we've talked about the Markovnikov's rule. I know it's not a new rule. You heard that also from your Ababio days. And we have given an illustration or an example of how the Markovnikov rule works. But there is an exception to the Markovnikov's rule. And this occurs when HBr specifically, it doesn't happen for any of the other hydrohalogens. It's only true for HBr. When it is added, when you're adding HBr to an alkene or an unsymmetrical alkene in the presence of a peroxide. Okay, in the presence of a peroxide, when you do such, then what you will have is a reversal. No, don't let me say reversal. Is an addition that is opposite to what you have for the Markovnikov addition. Okay, and so if we do that with the example on the slide, okay, you end up with the 1-bromo product. Okay, you end up with the 1-bromo product. So it's important. This takes place via a different type of mechanism. It's actually a free radical mechanism. Okay, but I'm not at this stage. I won't bother you with that. Higher levels, we explain that further. But the important thing for you to know is that if we're if there was no peroxide, bromine will add to the middle carbon. Okay? Bromine will not add to the terminal carbon. It will add to the middle carbon. But because of the presence of the peroxide, and because we're using HBr specifically, you end up with bromine adding at the terminal carbon or carbon 1. So you have the 1-bromo product. If you look at what I explained earlier, you see that it was the 2, I think we're using chlorine in that case. It was 2 chloro products we had. All right. So just to emphasize that again, that HF, HCl, and HI do not give the anti-Markovnikov addition. Okay, even when peroxides are present. For anti-Markovnikov, it is specific. We've only found it to work in the case of HBr or hydrogen bromide. Okay, that's the only case where we have found Markovnikov addition to work. All right, I think it's a convenient point for me to stop. We've looked at alkenes today, and we have come as far as looking at their reactions. We have a few more reactions to look at. I think we'll pick up from there early next week when I come back to class. All right, enjoy the rest of your day. Thank you for attending today's lectures.